Walk through a busy city, a crowded open-plan office, or a subway station, and your ears are subjected to a chaotic, overlapping barrage of acoustic energy. But put on a pair of high-end active noise-canceling headphones, flick a switch, and the chaos simply evaporates into quiet. Your brain tells you that those ear cups are acting as a thick physical barrier, blocking the outside world from getting in. But that is an illusion. To eliminate the roar of a jet engine or the chatter of a cafe, these headphones are actually generating more noise. Achieving quiet in the modern world requires an invisible, high-speed physics war, fought in the microscopic gap between the speaker and your eardrum. To understand how sound can destroy sound, we have to look at what noise actually is. Sound isn't a tangible object. It is a mechanical disturbance, a vibration that transfers energy by rippling through an elastic medium, like the air. This diagram shows a transverse wave. When you pluck a guitar string, the physical material moves up and down, perpendicular to the direction the energy is actually traveling. But sound traveling through the air operates differently. In this illustration of a speaker diaphragm, sound is a longitudinal wave. It pushes forward in parallel, shoving air molecules into dense bands of high pressure, called compressions, followed by thinned-out zones, called rarefactions. ANC works by detecting an incoming wave of compressions and rarefactions. The chip generates an exact duplicate. The system delays this duplicate, shifting it exactly 180 degrees out of phase. The original high-pressure peaks perfectly collide with the anti-noise troughs. They forcefully push and pull against each other with equal strength, mathematically adding up to zero. The technology weaponizes the physical shape of a sound wave to orchestrate its own destruction. This concept, known as destructive interference, isn't new. A German physicist named Paul Lug mapped out the exact theory and patented it back in 1933 to cancel sound in air ducts. But his theory hit a massive engineering bottleneck. To achieve cancellation, a system has to measure an incoming wave, invert its phase, and project the anti-noise through a speaker, all in real time. Analog electronics in the 1930s were vastly too slow to ever catch up to the speed of sound. By the 1950s, the deafening noise inside helicopter and airplane cockpits forced engineers to build the first practical, analog implementations of this concept to protect pilots from severe hearing loss. This is Dr. Amar Bose. During a 1978 flight, frustrated by the continuous engine drone leaking through his airline-supplied headphones, he began calculating the math required for modern digital signal processing, or DSP. The idea of active noise cancellation spent decades as a flawless physics theory trapped by sluggish hardware. It was waiting for the microchip era to provide processing speeds that could finally outrun a sound wave. This animation illustrates the physical problem. Modern ANC is a microsecond race against time. The headphone's processor must detect the noise, calculate the inversion, and deploy the anti-noise before that original sound travels the final fraction of an inch to your eardrum. To win that race, engineers rely on 3 different hardware architectures. In a feed-forward architecture, the microphone sits on the outside of the ear cup. This intercepts the wave before it breaches the plastic shell, giving the processor a crucial temporal head start. It's highly effective for blocking fast, high-frequency sounds. But a feed-forward system is effectively blind. Because the microphone is entirely on the outside, it cannot hear the final audio mix inside your ear. If the headphones shift on your head, the system might miscalculate and accidentally amplify certain frequencies. The alternative is a feedback architecture, which places the microphone inside the ear cup, right next to your ear. It listens to the exact same residual noise you do, creating a self-correcting loop that targets deep, low-frequency rumbles, though it struggles to react to sudden, high-pitched sounds in time. Premium headphones deploy hybrid ANC. By running both outer and inner microphones simultaneously, the processor leverages the early warning of the outside mic and the self-correction of the inside mic to neutralize the entire frequency spectrum. Microphone placement serves as a strict geometric constraint, dictating exactly which physical laws the headphone can exploit. Today, most of us aren't piloting helicopters or flying across the ocean every day. Our loudest environments are hybrid workspaces, open-plan offices, and busy cafes. Modern ANC provides a digital boundary for human attention, guarding cognitive bandwidth in a world that never stops talking. The ability to manufacture a zone of absolute quiet on demand provides a serious cognitive and economic advantage for anyone trying to focus. But look at this comparison, and you'll see the inherent weakness of traditional ANC. It easily predicts and neutralizes a smooth, repeating hum, like an engine drone, but it struggles to map an anti-wave against broadband noise, like a dropped glass or human speech, which is jagged and highly erratic. You cannot simply flip the phase of a sudden shout, because the mathematical pattern of human speech doesn't repeat predictably enough for a standard processor to map it in a fraction of a millisecond. To solve this, audio engineers are leaning on artificial intelligence. Instead of just blindly phase-flipping raw pressure waves, adaptive machine learning algorithms instantly identify the unique frequencies of human voices and isolate them from the background chaos. The software constantly measures the room, dynamically rewriting its own cancellation profile millisecond by millisecond to adapt to non-stationary, unpredictable environments. Every time you flip that switch on your headphones, you are invoking a physics theory written a century ago, executed thousands of times a second by advanced AI, to simply and quietly delete the noise of the modern world.